Alright, now, this is an ugly way to write this. Algebra comes in and says, holy shit, what are you doing? There's a better way to write that. Every single one of these looks like what, if I collect them? What is q times q times q times q? Yeah, so they all look like pq to the fourth, don't they? Every single one of them. And how many are there? Pq to the fourth plus pq to the fourth is
5 times
5 pq to the fourth. Alright, so let me write this over here. You guys, so if you understood what these are, now I'm just using algebra to kind of write it more concisely. And then our formula is going to pop out of nowhere here, right now. Alright. So what I've got is, now look at how this makes total sense. This is the probability that I get exactly one left-handed person, right? So how many P's are in the formula?
1.
Because that represents the one left-hander. So how many non-left-handers must there be? 4. So these exponents will always add to the total number of things you're choosing, right? Because you're going to break them into 2 groups. You're either left-handed or not left-handed. So if you don't have any hands, you're obviously not left-handed. So there's no way to not fall into one of those groups, right? I always have some smart ass trying to figure out, what about, no, stop it. What if I use my feet? Well, then you're not left-handed. All right. You with me? That's another reason why I don't say left and right, because I want to capture everything else. All right. So just, and where did this number come from? Be very careful.
From all the possible outcomes?
All the possible outcomes. Not the 5 people, believe it or not. Because if I wanted the probability of 2 left-handed people, that list is going to be longer than you might think. Because the first 2 could be, or the middle 2 could be, or maybe the first one and the last one. And that list is going to be a little bit longer than you might think. It's not going to be 5 long, it's going to be 1. Alright, so all we're missing then, so if I would have said, alright, well first off, let's actually get what this number is, just to close the loop of this problem. What is this number? What was P? What was the probability of a left-handed person?
1, 5.
I told you
11%.
11%, so that would be 0.11, right? Never put in, math doesn't understand percentage. Percentages are a completely human constructed thing. Math wants the actual freaking number, it's 0.11. And then, so that's 0.11 to the first. And what was the right-handed people, or the non-left-handed people?
89.
49.
89 to the fourth. And what do you get when you plug that in a calculator?
0.345.
That's exciting. 3, 4, 5, 6. Double check that.
Yeah.
It's not that I don't trust you. It's just it's always good to cross source. Alright, cool. So what does that mean then? Physically, what does that mean? Yeah, I got almost a 35% chance that if I pick 5 people, one of them is going to be left-handed, right? I like it. Alright. So, let's try to construct what the formula is going to look like then. Let's see. Let me leave this up here. I want to reference both of these somehow.
So is this binomial probability because you're always comparing 2 things? Is it always going to be 2 things, or?
Binomial probabilities have to have, well, let's see. Let's list some things. They have to have exactly 2 outcomes. But like I said, if it matches what you're kind of interested in, you can make anything binomial. A die has 6 sides, but the outcomes could be a 5 or not a 5. Right? So if it matches what you're kind of working with, you can make anything binomial. Okay, cool. I like it. There must be n trials, a certain number of trials. So in this case, there are 5 trials. That means just picking a person. Every time I pick a person, there's a certain probability they're left or right-handed. So if I was talking about flipping a coin 100 times, and what's the probability I get exactly 50 heads, there would be 100 trials. Every trial would be me flipping a coin. You with me? So there must be a closed set number of trials. There must be P and Q, and they have to equal 1. The probability of success and probability of failure have to be 1. And every trial has to be independent from the others. Otherwise, I couldn't continue using the same letters P and Q. They would change, and that would so desperately suck. Q1, P2, Q1, Q3, Q8. No. Because those are the things that are required for binomial probability. So let's figure out what the formula is. So for right now, I'm just going to put the first thing that shows up in the formula is how long the list is. That's the one piece of this that I'm okay with just using the calculator for, because the calculator is built to count shit, right? So believe it or not, I don't know if you've ever heard this, but if you had a pizza that you could have like 8 toppings, how many pizzas could you create? In the millions. This is completely against what our brain says should be true. Because you can have none of the toppings, just cheese pizza, right? And I mean cheese, you just have bread. I don't know if they'll do that. Right? Bread isn't bread. All right, yeah. Or you can have one of the toppings, any of the or you can have any 2 of the toppings, any 3 of the toppings. Then you bring in like extra of some toppings or less of some toppings. Before you know it, you're in the millions. Holy shit, right? Okay, so this is part of the formula. Is that first number is how long the list is times P to the what? What was this number here? Successes. The amount of successes, whatever the success is. And again, success could be a squirrel with rabies, whatever I'm looking for, right? So we're going to call that X. So X is the number of successes. What did we use X for before?
Variable.
The variable. And the variable here is the number of successes. So it could be 0 up to whatever, however many times you did something. So I could get 0 up through 5 left-handed people because I picked 5 people. And then it would be Q. Now here's the weird part. So this is times Q to the what? Failures. So exactly how many failures would I have? Well, how many total things? What do I always use for the total number of things? N. So here's the weird part. How did I get 4? I did 5 total things minus 1. So it's going to be N minus X. So let's fill in that first part. That's the only thing we don't know. And then we're going to do a couple examples. And then, of course, you know me. I have a little handout that I'm going to let you guys work on. So here's the... Let's fill in the first part. If you want a calculator, some up here. Because we're going to be using that bad boy. Sure, I get them back. Otherwise, they'll dock me. They'll dock me. I didn't want to dock it so far. All right. So if you got your calculator, and here's the idea. It's kind of nice how you say this in English. If I had 5 people, let me just say, how do I say this? Yeah, exactly. If I had 5 people that I was looking at, how many ways could I choose one of them? 5 ways, right? So if I had 5 people, how many ways could I choose 2 of them? We don't know yet. We'll calculate it here in a second. But the way I would say it, 5 people choose 2. So it's exactly how I write it. 5 choose 2. Man. I'm just trying to get it into the format that the calculator understands. So what that means is if I put 10C7, the calculator would tell me if you had 10 things, how many ways could you choose 7 of them? A lot. The first 7, the first 2 and the last 5, the first 4 and the last 6, the first, or whatever. I forgot what numbers I was using. But you kind of see there's a lot of ways, right? So here's how you put it in the calculator. Go away. Color scheme. All right. So watch this. The most important button for us, of course, is stat, but the second most important button in any math class is the math button. If you hit the math button, what do you think is important for me right now? What's your gut tell you? Which one of these?
Probability.
Yeah, probably where. So don't do anything yet. Don't select anything, but just notice which one of these am I talking about right now? The third one, right? The second one's National Public Radio. This is I don't know if you guys. Oh, we don't talk about combinations and permutations in here, but has anybody ever heard of combinations and permutations? Okay, and they just reference the number of ways to choose something if the order matters or if it doesn't matter. But don't. That's what the P really is. Just to give you the technical definition, not National Public. But the third one is combinations, but I just call choose because that's exactly what we would say. If I had 5 people, how many ways could I choose one of them? So that's what I could say the C means. It doesn't really, but screw it. It's good enough. So here's how I would put in there. I have to go back to the screen, to the main screen. So if I want to do 5 people, and I want to choose, so now I go to math, probability number 3. So 5, choose 2. It's only 10 big. It's not that big. You with me so far?
Yeah.
All right. Now, real quick, just to show you, if you did 8, let me just show you. Now I'm curious if I remember this right. If I use the permutation, this should be, well, it's only 40,000. I can't remember what it was. That would be related to the pizza thing. 40,000. There's somewhere there's getting millions. I guess there's more than 8 topics in there. All right. Anyways, forget it what I just did. It's fine. So what if I had, so I desperately want you to see, and you guys just missed all that. Screw it. Let me do it one more time. Go in there. So let's see, if I wanted to do 10, choose 7, 120. There's 120 ways to choose 7 people from 10. You guys kind of think that's what that means, right? So what would 10 choose 0 be? Don't do it. Think about it. What would 10 choose 0? What does it mean physically? I got 10 people. I want to choose nobody. So how many ways can I do that? 1 way. I choose none of you. Right? There's only one way. Not like, and then I can go, I choose none of you. I choose none of you. No. It's just one way to do it. I don't take anybody. Sure enough, if you do 10, let me just cut to the chase. If you hit second enter, if you had to do a bunch of these, you can just go back and edit it. 10 choose 0 is 1. Anything choose 0 will be 1. What if it was 10 choose 10? How many ways could I choose 10 people if I had 10? Just one way. Take everybody. So 10 choose 10 would be 1. All right. So let's do a problem. I desperately want you to see how this formula sets itself up.
What if it was a different number times 0? Or if we were to put a different number and choose 0.
Anything choose 0. Try it. Do 120, choose 0. All right. So let's try a problem out. Crazy. Because again, I don't care how many ways can you choose nobody? Choose nobody. There's only one way. Choose nobody. How many ways do you choose 1 if there's 120? 120, because I can pick the first guy, or the second guy, the third guy, all the way to 120. Yeah. Well, 120 choose 2. Holy shit. Well, now that you got me here's 120 choose 2. Can I do this? Yes. You can do it, Jack. 120 choose 2. 7,140. So it grows a lot quicker than we expect, because it could be the first 2, or the middle 2, or the third one and the 80th one, or holy shit. Right? And this is sort of related to, I don't know if you ever heard this, but if you shuffle a deck like 7 times, it's incredibly likely, very high probability, that no deck in history has ever been exactly in the order that that deck is in right then. That'll really mess with your brain.
That's cool.
I know it's cool. So like there was a show and the guy said, I'm going to do something that's never occurred in all of history. And he shuffled the deck like 7 times and he's like, there's been no deck ever. The probability is so low that it was, that it most likely it never was. That'll really freak the hell out, right? I'm sorry, who did I? Yes?
How do you, like, going up?
I'm sorry?
Like, how do you copy it?
Hit second enter. So if I hit second enter once, it'll pull up the last thing. Oops, sorry. If I hit second enter a couple times, it'll pull up the thing before it. And I think in the newer version, you just have to hit the up arrow, I think, in the newer RAM. If you have one of the ones where the square root symbol grows or something, you just have to hit the up arrow to edit. Right. Okay. If you have one of those nifty skinny ones with the backlight, yeah, that's what I'm talking about. Look at that. Look, any Matthew or just salad or sorry.
Oops, it cost me $150.
Damn, holy shit. Well, some of my saliva just went right. All right.
Moving on.
So let's try a totally different problem. Obviously, a binomial probability problem. So let's say that 82% of Grossmont students. What do you think? Give me something. My creativity is low. What do you think 80% of Grossmont students have done?
Graduate.
Graduate. Okay, cool. That would be so awesome if that was true. Our little scorecard for the state would be nice. So let's pretend like this is true. All right, we're in a parallel universe where this is true. And of course, this is nothing about the academic potential of anybody. This is stupid. People in community college, very often, they have a lot of shit going on. And they come in and out. Sorry. It's just the state wants to define success for schools and to pin our finances on that. I'm like, how can you do that when anybody, they just had, something happened in the family, had to leave. They transferred and they don't tell anybody. Who knows? All right, I'll let it go. Sorry. There's nothing to do with this. And I want to know the probability, if I pick, let's say I pick 14 Grossmont students. What's the probability that exactly, what you got, Jeff? I don't know, Jeff. Exactly 11 graduate. So first thing, a really, really good idea is to summarize everything you know. So what's this? But what is it?
The success rate.
Cool. So what variable does it go with? P. I like it. So P is 0.82. So what's Q?
180.
Good. And real quick, this was P because it's what I'm looking for, right? If I said probably exactly 11 don't graduate, that would have been P. And that's a little important because it changes your formula maybe a little bit. You got to be careful. You want everything to match up.
How'd you get 18? Oh, wait, never mind.
Cool. These have to add up to be 1.
Mm-hmm.
What's N? 14, because I got 14 trials. Right? And finally, what's X? I want 11 successes. I like it. So now I can just plug and chug. And this is beautiful how this sets up. If I've got 14 people, how many do I want to choose in this problem? 11. Which means how many successes will I have?
82.
No. The success is 0.82. That's the success, right? How many of them will I have? I'm going to repeat myself a little bit, right? 11 of them, of course. So I got 14 people. I want to choose 11 to be successes. So I got 11 successes. So how many failures? 3. So the formula makes this look a little more disgusting than it really is. It's just that power is going to be whatever's freaking left over, right? But the formula's got to be general, so it looks a little bit harder, but it's just the number that's left over.
Wait, where'd you get the 30 from?
If there's 14 total people and there's 11 of them here,
So
the other 3 have to be there. And that's what 14 minus 11 would be. Okay, yeah, so that's the formula.
For the card that's for how long it is, how come you choose 11 instead of just like 14? like how in the formula it says like how long it is.
Yes.
How can we put like to choose 11?
Well, this whole thing, that whole thing, if I plug this in the calculator, will tell me how long the list would be if I made it. And I don't want to make this list. Just help me out. What's 14 choose 11? How long would the list be?
364.
All right. And I don't really feel, just in case you need to, here's, yeah, there's Jeff. What are you doing? 14 choose 11. So that would be sort of easy to forget somebody if I'm making a 364 entry list, right? No way. I don't want to do that. No. So I really want you to understand, why was this one a 5? Because there are 5 ways to do this. So I really want this to make sense. If I let the calculator count the list for me, that's the one part that I'll let happen. I'm not going to make you make the 364 list. That's just stupid, Jeff. Don't do that. Okay, I won't. So I'll let the calculator do that for us. But the rest of it, I hate that this book doesn't show you, because the formula tells you why this makes sense. It just sets itself up. This many of these, and there's that many ways to do that. So if you just plug the whole thing, actually when you do this, you can just put it in here all at once. So 14 choose 11 times 0.82 to the 11th power times, no, Jeff, that's not times. There you go, buddy. 0.18 to the 3rd power. Those are the other 3 people. So I get 2, 3, 9, 3 roughly. 20, almost 24% chance. So out of any group of 14 students, I have an almost 24% chance, almost a quarter of a chance, that I'll have exactly 11 of them graduate. Course 1 students. That's what that means. Okay, so, do you guys, this formula is so nice. It sets itself up. So let me give you this. Let me see if you guys understand what I've done here. Hey. Oh, yeah. For a second I was thinking that. Hey, so how you been doing, man?